The groundbreaking 12-tone technique championed by Arnold Schoenberg, Alban Berg, and Anton Webern during the early 20th century saw its momentum sustained by subsequent vanguards of serial composition such as Boulez, Stockhausen, and Babbitt. Inspired by this innovative approach, luminaries like Stravinsky, Copland, Harrison, Andreessen, and Adès, to mention but a few, have since ventured into the realms of serial experimentation. The building blocks of these revolutionary techniques are tone rows, sets of musical pitches that adhere to a fixed order, typically encompassing all 12 pitch classes of the chromatic scale. Within the robust toolset of Music21, a range of functionalities offer composers the means to delve deeper into the intricacies of tone row manipulation. Let's begin by importing Music21, after which we can encode a tone row by employing a row object, a specialized stream accepting a sequence of strings or integers as its parameter. As an illustration, we'll consider the row from the string trio Opus 45 by Arnold Schoenberg. Let's define a variable named trio row and initialize it with a row object. We provide a list of strings to denote pitch classes, adhering to the customary representation in Music21, whereby a sharp may be depicted using a hash symbol, while a flat can be signified by a minus sign. An alternative strategy to represent the ordering of pitch classes is to leverage integers ranging from 0 to 11. Specifically, we assign the value of 0 to C natural, while C sharp assumes the integer 1. Ascending through the octave, each successive pitch class within the scale increments by 1 until reaching B natural, designated as 11. This numerical approach enables us to seamlessly capture the intricate intervallic relationships inherent within our row. We can call trio_row.show to display the row as a musical score. Within the context of 12-tone technique, this fundamental incarnation of the row is commonly referred to as the prime form. By applying transposition along with specific operations upon it, composers can generate multiple derived versions. Inverting each interval within the row engenders an inversion. Reversing the order of pitches creates a retrograde form. Moreover, the simultaneous application of both retrograde and inversion operations yields the retrograde inversion. In Music21, we can invoke the zero-centered transformation method to create versions of a row derived by such operations. The method accepts a string parameter that specifies the desired transformation type, represented as P for prime, I for inversion, R for retrograde, or RI for retrograde inversion. Additionally, the method expects an integer parameter representing a pitch class, which serves as the basis for the transposition. Abiding by the zero-centered convention in 12-tone theory, the prime and inversion transformations begin on the specified pitch class, while the retrograde and retrograde inversion transformations will end on the specified pitch class. Now let us consider how we might employ Music21 to effectively exploit tone rows for composition within a Python program. We'll define a main function, which, following standard practice, we shall call at the bottom of our program with the conditional if name equals main. This convention instructs the Python interpreter to invoke the main function when directly executing the program. Within our program, we shall leverage transformative operations applied to our tone row to derive a linear sequence of pitches for composition. The order of transformations could be determined by a myriad of potential strategies. We might opt to incorporate various constraints or base our decision on an analysis of the row's intervallic structure. However, for the purpose of this demonstration, we shall embrace a randomized approach. We can access a variety of functions that allow us to utilize chance and unpredictability by importing random from the standard Python library. We'll create a function named random row transformation that takes as input a tone row object and returns as output a randomly transformed row. Within this function, we'll need to select a row form from prime, inversion, retrograde, and retrograde inversion, represented as the strings P, I, R, and RI. To return an element at random from a list of these options, we can use random's choice function. The chosen element will be assigned to a variable called row form. To select the pitch class onto which our row will be transposed, we can use random's randRange function, which will select a random integer from a specified range. We'll create a variable called row index and specify a range of 0 to 12. To complete the function, we can use the zero-centered transformation method, providing it with row form and and row index and returning its result as our output. Now let's test this within our main function. We'll declare a variable called melodic row to which we'll assign the result of applying random row transformation to our original tone row. We can view the notated result with melodic row.show. The output of our function, while aligned with our objectives, is limited solely to pitch series transformations. To generate compositions of greater interest and depth, we must broaden the scope of our program to encompass additional musical parameters. Consequently, our focus will shift to how we might manipulate and integrate rhythmic elements within our pitch series. One avenue we might explore to achieve this is the application of serial techniques to the domain of rhythm. Interpreting the 12 integers employed to represent pitch classes as durations is a straightforward process. We initially must establish a minimum duration, such as a 30-second note, which will be assigned to the integer 0. We increment the duration by another 30-second note for each subsequent integer to form a durational series. Leveraging this scale, we can generate a durational row and apply the same operations we utilized on the tone row to manipulate it. In a program, we shall introduce another function, serial melody, to generate a melodic line based on two randomly selected transformations from our row. One transformation will determine the pitches, while the other will dictate durations. The function will expect a tone row object as its initial parameter and a float as its second parameter, representing the minimum duration for the notes comprising the melody. Additionally, it will require a tuple of two integers as its third parameter to specify limits for the lower and upper octave values of our melody. This will help to infuse further variety into the melody through random octave displacements. The function will return a Music21 stream object, which represents the sequence of musical elements within our melody. To create the function, we'll first initialize a stream object called melody, which will eventually contain our serial melody. To determine a pitch sequence, we'll invoke the random row transformation function, which we previously defined, passing the row argument. The resulting transformed row will be assigned to a variable labeled pitch row. We'll create another variable called duration row and call the random row transformation function with the row argument again to yield another randomly transformed tone row object. However, in this case, we are solely interested in the integer representations of its pitch classes. To access these integers, we will utilize the pitch classes method of the tone row, which will provide us with a list containing the desired values. We'll proceed by creating our melody within a for loop. We'll iterate over the elements within pitch row with for I, pitch class in enumerate pitch row. Within each iteration, we'll create a duration object and assign it to the duration attribute of the note object represented by the pitch class variable. We'll create the value of our duration by multiplying the duration unit argument by one more than the corresponding element in the duration row. For example, if duration unit is 0.125, which means a 30-second note, and duration row at index I is 3, then we multiply 0.125 by 3 plus 1 to create an 8th note. Next, we randomly assign a value to pitchClass.octave using the randint function from the random module. This function requires two arguments, the lower and upper bounds for a random integer to be generated. In our case, we'll utilize the octave range argument to specify these bounds. Since the octave range values are stored in a tuple, we need to unpack them using an asterisk. After this, we use melody.append pitch class to append the note object represented by the pitch class variable to our melody. After looping over all elements in the pitch row, we return melody. In our main function, we'll create a new Music21 stream called treble line. We'll call the serial melody function, passing in the tone row object a value of 0.125 to represent a minimum duration of a 30-second note, and as the third argument, we'll specify the octave range from 4 to 6. We'll append the result of our treble line and call trebleline.show to view our notated melody. To generate a melody of extended length, we can utilize a for loop to repeatedly append the results of the serial melody function. For example, by specifying for I in range 5, when running the program, we will generate a melody that is 5 times the original length. After successfully implementing a basic version of a program to generate compositional material using serial processors, there are numerous avenues we could explore to enhance its capabilities and sophistication. For example, we could impose additional constraints or logical rules to determine our selection of serial transformations to provide more control and structure to the generated material. Furthermore, we could devise methods to incorporate rests or explore chordal textures, especially if our composition is intended for instruments capable of playing multiple notes simultaneously, such as the piano. We also might extend the serialization process to encompass other musical parameters like dynamics and articulation. With these possibilities in mind, this current implementation serves as a solid foundation for further exploration and refinements. Thank you for watching. If you enjoyed this video, please like and subscribe, and leave a comment with any suggestions or requests for further topics related to Music 21.